So in this video what we're going to do is look at the effect of changing the concentration on the EMF of a cell. So we mentioned at the beginning of the pack that EMFs are measured under standard conditions of a temperature of 298K, a pressure of 100 kilopascals and a concentration of 1 mole per decimetre cubed. And what we're going to look at in this section is what effect changing that concentration would have on the value that you would read on that voltmeter. So can you make your battery produce more volts if you change the concentrations inside it? And I think the thing you've got to be careful not to fall into the trap of is just assuming that if you just increase the concentration you'll increase the voltage, because that's not necessarily true. We're going to have to use Le Chatelier's principle. We're dealing with equilibriums. So if we remember that Le Chatelier's principle says that a position of equilibrium will shift to oppose a change. So what we need to make sure we understand is what is happening in our cell. So let's just have a look at our copper zinc cell again. Let's break it down. Let's think about what we've got. We've got our left-hand side, and on our left-hand side we know that something is oxidised. And on our right-hand side that something is reduced. So what is oxidised? Well, if we have a look at it, we know that the zinc is oxidised, and then on our right-hand side that the copper 2+ ions are reduced. So looking at a standard representation, we know that. We could have got that from the numbers as well, because the most positive one gets to go the way it's written as a reduction, so it's going forwards. So we would know that this reaction would be going forwards because it's more positive, and this other one would be going backwards because it's more negative. Zinc is being oxidised, copper 2+ is being reduced. So according to Le Chatelier's principle then, so if we go back and we have a look, if the concentration, remember the square brackets means concentration, of copper 2+ ions, they're here. So let's just make sure we know what we're doing. We've got, if this is increased greater than 1, the equilibrium will shift which way? So we're adding to the left, so according to Le Chatelier's, we're going to shift to oppose the change. We're going to shift right to remove the added copper 2+ ions. And that means that the value, which is 0.34 at the moment, the value is a measure of reduction. If we're getting more reduction, then it's going to become more positive, and copper 2+ ions will gain more electrons. More reduction is going to happen. So here we were sitting on this number line, and the zinc 2+ is not changing, and the copper 2+ is now becoming more positive. So all of a sudden, we don't know where we're going to, but we're going further right. Now what has happened to the size of the overall gap? If we get more reduction happening, so more of this converting to that, so more reduction happening, then the value for the whole cell is going to increase. The gap between the two is bigger. So in an exam, if we increase the concentration of copper, because we're going to get more reduction, so the same amount of oxidation, but more reduction on the right, the difference between the two is going to increase, and so we'll get a bigger value. If conversely we decided to reduce the concentration, the equilibrium would now, so we're having less copper 2+ on the left, the equilibrium will shift left to replace the copper 2+, and it will become less positive, because we're still going to be doing reduction, but there's going to be less of it. So it will gain fewer electrons. So what you need to be careful of is, although when we're talking about this equilibrium, we're saying it's going to shift left, we're not saying it's going to start going backwards. We're saying the position of equilibrium was here, and now we've shifted left. So we've got more copper 2+ and electrons than we had before, but we haven't gone backwards. We are still moving forwards, but just not as well. So it's going to gain fewer electrons. There's less copper 2+ there, so we're going to gain fewer electrons. And if we gain fewer electrons, less reduction is happening, then our line is going to shift to the left, just like we said there, the equilibrium is going to shift to the left, and the gap between the two is going to decrease. Okay, so that's looking at our positive half cell. What if we make those changes to the negative half cell? So if we increase the concentration of the zinc, so if we make there be more Zn2+, then remember that the equilibrium for Zn2+ looks like this. Zn2+ puts 2 electrons in equilibrium with Zn, and we had a value of minus 0.76 volts. If we increase the zinc 2+, then the equilibrium is going to shift right, that equilibrium that we're talking about, and the E0 becomes less negative, but now we have to remember that actually in this reaction zinc is being oxidised and losing electrons. So if we are shifting right, we're going to have more zinc, and zinc will be losing fewer electrons. So before we were losing electrons, and now because our equilibrium has shifted to the right, so before we were going backwards like this, we were losing electrons, but now we're shifting our equilibrium to the right, so we're not going backwards quite as much. We're losing fewer electrons. I'll put that on here. We've shifted the position of this equilibrium to the right, and the gap between the two is smaller. So increasing the concentration of zinc leads to a decrease in the cell potential. If we were to do the opposite then the equilibrium will shift to the left. If we were to decrease the concentration, it's going to become more negative because we're going to release more electrons. Remember, the zinc is losing electrons, so it's going to lose more electrons. Our position of equilibrium is going to shift to the left, and the gap between the two is getting bigger. So using this number line can really help you, but you do need to remember that the thing on the left loses electrons and the thing on the right of the cell gains electrons. So answers need to be relative to those principles. Notice that once we have changed the conditions, we're not now under standard conditions, so the standard state symbol sign has gone. And the last little bit about this then to remember is that anything we've done in this electropotentials pack assumes that we're doing things under the standard conditions. We're measuring an amount of electrical energy flowing. It's telling us about the electrical energy, but it's telling us about the equilibrium, but it's not telling us about the rate. So despite all the information saying these two things should react and produce electrical energy, it still might not, because our activation energy might be too high. And so our rate might be too slow. And also we might not do them under those standard conditions, quite hard to maintain those, so they might not be the right values anyway.